So we found some drawback of Taylor's and Picard method, which motivated, I mean, the researcher at that time to develop some other method. What was the drawback we were facing that time? That these methods are biased towards the initial point of the domain and does not give the good result if they are, I mean, we are going far from the initial point. It means that if we wish to have long time simulation, so then result will be, it's, am I audible, ma'am?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So then these method will not provide us the good result. So then there is a quest of that to develop some method whose convergence, I mean, does not depend on the I mean the or accuracy does not do not depend on the initial point of the domain or the point of the domain. They should give you the uniform accuracy throughout the domain, and then we
फॉर्म में अच्छा इधर भी LHS में भी रहेगी यहाँ क्या होती है y
hello.
है ना और
Yes, sir. Yes, sir.
Yes.
Some disturbance is coming.
Yeah.
Okay.
We manage it, sir.
Okay. So in that case, what we did, rather than approximating the thing on the entire domain, we I mean divide domain into the sub intervals and then taking approximation on the smaller domain, and this concept works and gave birth to the step marching method or discretization method. So now we will develop the step marching method, and I think I also explained that the step marching method are divided into two classes. Single step method or one step method and multi-step method. If when we are, I mean, approximating the next value, if we are using
This is not coming.
hello.
Yes, sir. Now you're visible.
Now it's coming.
Audible.
Yeah. So if it is a single, I mean, if we are using just the preceding value to calculate the next value, so in that case we are using only one step for the prediction. But at the same time, when we are going, I mean, far from the initial point, so at that time we have more than one value. And as I told you that for the prediction, if we have more than as much as information we have, so that will give us better and better result. Basically, if you use, when we are using the one step method, so then we have two information. Am I right? If we are using the single step, in that case, suppose this is at xi and this is xi plus 1. So we have here two information we have, because we may know or we may utilize that, and using the two information we can use the linear approximation. Am I right? Because to fix, when we take the linear approximation, so basically we approximate by a straight line, say ax plus b, and to fix I mean a straight line, so we need two parameter to be fixed. Am I right? Otherwise we will have a infinitely many lines. So to fix a or to define a unique line, so we require two information. Am I right? If we want to approximate the things by a higher degree polynomial, say second degree polynomial, so in that case ax square plus bx plus c, bx plus c. In this case we need to fix three parameter a, b and c. Am I right? And we know, I think who are working in a, or maybe I mean we are a student of mathematics, so all of us are aware there is a theorem by the Weierstrass theorem in the approximation theory. What it says that for giving any tolerance, epsilon, if your function is a continuous, so then corresponding to this tolerance epsilon, we can find a polynomial of degree n such that the distance of the function from this polynomial is less than epsilon. So what does it mean? It means that we can I mean approximate a function by a polynomial with desired accuracy. Am I right? So as we are increasing the degree of the polynomial, so then we are getting better and better approximation to the function. So this thing is clear. So basically when we are using, I mean we have two information, so in that case we can approximate the function by a straight line. If we need to have the better, I mean accuracy, so we need to have more information. Or fortunately when I'm approximating or predicting value at xi plus 1 node, so at that time I have information up to at the xi minus or I minus 1th node, I mean I minus 1 nodes. So if we are using, I mean more than one, if we are using the 3, suppose I wish to approximate the function by the quadratic polynomial, so then I need to use this one also, xi minus 1. So then the method I mean obtained in that way will be two-step method. If we are using the k I mean step, so in that case the method will be k-step method. So first we will start from the single step method, and then we will move to multi-step method. So
Hello, sir.
yeah, hello.
Sir,
Hello.
sir, I need to ask
tell
one
me.
thing.
Yeah,
Sir, you said better approximation. We need to have high degree. Is it so?
yeah, your voice is not clear. Please repeat.
Sir, for better approximation. Sir, as you said that for Weierstrass theorem, we approximate continuous function with poly. Hello.
You just type the.
Sir, am I audible?
mean, yeah, now you are audible, but in between it's I mean just disturbance visible there. Yeah, you are saying that.
Sir, you said that. Sir, you said that for better approximation means Weierstrass theorem function can be approximated. For better approximation, we need to have high degree.
Yeah, of course. I think it's not I am saying it's a Weierstrass theorem says. Am I right? If you are increasing the degree of the polynomials, you have, your error will reduce. It's fine. Rather
Okay,
than
sir.
the state line, if you are approximating the function by a quadratic polynomial, so you will have the better result.
Okay, sir.
So now how we will use this concept while we are doing that, I think now this thing is clear that rather than approximating the the function on an entire domain, so what we do, we will discretize the domain, and in small part we will make the approximation. So now we have this initial value problem, y prime is equal to fxy y at x naught is equal to y naught. So what we did, we just integrate this, and we converted this into an integral equation rather than the differential equation, that yx is equal to y naught. Y naught, but now we will do the little in a different way. So now we have discretize our domain. So now our domain, we have discretized our domain. My drawing is very rough. So suppose this is our domain. We have described this. This is say A to B, and maybe for time being we kept the uniform steps. And dot in that way. Suppose this is the xi node, and this is xi plus 1. So now rather than integrating from x0 to x, now suppose we integrate after discretization, we integrate this differential equation from xi to xi plus 1. So please do that. I'm just writing the final result, y at xi plus 1 is equal to y at xi plus integral xi to xi plus 1 f y xy dx. This thing is clear. So we have converted our differential equation into an integral equation. This thing is clear. So now this integral is making us problem. So now we will visualize that basically we want to integrate this function, the function fxy from xi to xi plus 1, means in this interval. Suppose this is xi start. I'm just taking this interval. This is xi plus 1, and then we will take we will vary I, so we will get the result. So basically what is this integral? If you do, just we are talking about this one. So what is f is nothing but y prime of x, means another function of x. So it's a implicit function of x. So I can write this represent by gx. Suppose gx is equal to y prime x. If y is a function of x, so then of course its first derivative it also will be a function of x. So our now problem reduced to find this integral. Integral from xi plus 1 xi to xi plus 1 of gx. Am I right? Gx dx. And we know that what is basically integral. Integral is nothing. Suppose this is the curve of g. Suppose this is a curve of g, and so basically my objective to find the area under the curve, under this curve between xi and xi plus 1. Am I right? So my area to find to find this area. So how we can do that? Do we know the area of this geometry? The answer is negative. Yeah, we don't know. And what problem? These are the straight line. Basically, these are the side straight line. Don't confuse. I think you people will not confuse. These are the straight line side. So which one is creating the problem here? Here is this curve gx is creating the problem. So what we will do, we will approximate this curve by the straight line. So suppose I approximate this curve by this straight line. Am I right? We can change the color of, yeah. Suppose we approximate the this curve by this straight line. Am I right? So now we know the area of this geometry. Yeah, because now it's a rectangle. What is this length? This length is f at xi, which I am denoting fi or gi. I'm denoting this gi is equal to g at fxi. And what is this height? This height basically gi plus 1. No, sorry. This is this height. Am I right? This is gi plus 1. So now tell me what will be the area of this curve? This one, from here to here, and this. Yeah. So tell what will be the area? That is equal to height, height, this this one add into this distance. So gi, and suppose this is, we are taking the uniform mass size, so this is h, so h times gi, am I right? Or g at, you can say that g at h times f, sorry, g at xi. This thing is clear? And what is g at xi? G at xi is y prime at xi. What is y prime at xi? That is equal to, but this is not basically equal to, this is approximately equal to, because now we made the approximation. So this is approximately equal to h times fi. This thing is clear? Yeah. So in that case, what would happen? That y at xi plus this y at xi plus this is h times fi. This thing is clear. But what is a problem we are facing here? Now this equality becomes inequality. Am I right? This equality becomes inequality. So then what we should do that? So we keep that, okay, make it equal sign. Let us assume equal sign, or we can say that we make another notation. We make another notation rather than y at xi plus 1. Now I am using, I am calculating right hand side. What is right hand side? Y at xi plus hfi, and whatever I'm getting, I'm denoting that by yi plus 1. So you should not confuse. In your notebook, you might have seen in many or in most of the notebook that yi is equal to y at xi. No, this is not right. So yi plus 1, what is yi plus 1? Yi plus 1, whatever we are getting on the right hand side, that is. So yi plus h f i, and this yi plus 1 or yi are the approximation to y at x I. This thing is clear. So in that way, this is known as this formula is known as Euler's forward, Euler forward formula. Am I right? Is there any other way to do the same thing? Yeah, we can do other way also. For example, now rather than this way, we approximate this curve from the upper side, and now this is the rectangle. This will be the rectangle. This thing is clear. And in that way, I mean, going in the same way, so in that way we will get that yi plus 1 will be equal to, tell me what value we will have. yi plus h times, and can anybody tell? Now we are taking approximation from the upper side. Rectangle and rectangular will be there. So h into this height. So what is this height? This height is basically gi plus 1. Gi plus 1 is nothing but fi plus 1. Am I right? So in that way we will have we will have Euler backward formula. I plus fi plus 1. This is known as the Euler backward formula. Am I right? Also, first is also known as the explicit Euler method. Explicit Euler method. And this is known as the implicit Euler method. There are two nomenclature to each: implicit Euler method. Why it is? So first we should analyze that why we called the first one is the forward Euler method and the second one is the backward Euler method. Anybody can answer? Please answer. Hello, am I audible?
Yes, sir.
Yeah, so why we call forward Euler method and backward Euler method? Any participant should answer. Because what we are doing in the first case, we are taking the terminal value, and that we are basically stretching that terminal value in the interval in the forward direction. So that is this by this reason this method is known as the forward Euler method. In the second case, what we were doing, we are taking the final terminal or this terminal value, the final one, and stretching back in the backward direction. So that why it is known that the second is known as the backward Euler method. Yeah, and also I said that the first one is known as the explicit Euler method and the second one is the implicit Euler method. So why hello? Yeah, so can anybody answer that why we call the first one is the explicit Euler method and the second one is the backward Euler method? Can anybody answer? Hello?
Hello.
Because basically what is unknown? Unknown is why the unknown is y I plus 1. But if you look the first formula, in first formula, what's happening basically? In first formula, yi plus 1 is given explicitly because the previous value is known to us. Yi is also known to us, and f at
But your voice is not coming.
Hello. Hello.
It is coming
Now
now.
it's
Sir.
audible. So now it's audible.
Okay.
Sir, screen is not.
Sir, your screen is not visible. Please share it again.
Yeah. Now it's fine.
Yes, sir, it's visible now.
Yeah.
So if we have this yi plus 1, yi plus I plus 1 is equal to, I think you should I mean,
Sir, we mute all the participants. Sure. Sir.
so whom I mean voice is coming.
Sir, please unmute yourself now.
So you're not audible. Hello? Sir, Kapil sir, you're not audible.
Sir, you are on mute.
Okay, now it's fine.
Yes,
Hello.
sir. Now it's
Hello.
okay,
Sir, yes,
Sir, it's
sir.
okay now.
Hello?
Yes, sir.
Okay. Yeah, so yi plus 1 in the second case, I plus 1 is equal to I plus 1 is equal to yi plus f at xi and yi plus 1. So I mean here unknown, if you look in the second case, in the first case, the unknown sitting on the left hand side and everything known is the on the right hand side. So that's why this formula is known as the explicit Euler method. In the second case, unknown is written in the equation in implicit form. We don't have any procedure by which we can take unknown on the left hand side and everything is known on the right hand side. So that's why this is known as the implicit Euler method. So this thing is clear. Implicit Euler method, and this is explicit Euler method. So that was the reason behind the nomenclature of these two methods. So now again we are doing what else we can do when we are approximating the area under the curve. Suppose this is the curve. So one way is that we have approximated in that way this area by this green one, and another in the explicit we have approximated this geometry by another rectangle, like this. This one. So is there an other way also to approximate this geometry by a geometry whose area is known to us? Yeah, we can do that using the trapezium. We also know the area of the trapezium. Am I right? We know this height is, so what is the area of trapezium? This height is, this is the trapezium, and this height is Fi, and this bigger height is of the trapezium is Fi plus 1, and the distance between the two parallel side is h. So then what will be the area of the trapezium? Then the area of trapezium yi plus yi plus, so area of this trapezium. So tell me, anybody can answer? H times the average of the parallel side. Am I right? So the length of parallel side is Fi and Fi plus 1. So the average will be, yeah, Fi plus Fi plus 1 divided by 2. Am I divided by 2? So this is the third one is the plus is equal to yi plus h by 2, if you remember, h by 2 fi plus fi plus 1. So this is the area of the trapezium, and in that way, whatever we are getting, basically the formula is known as the trapezoidal rule. This is known as the trapezoidal rule, and of course, in this case, it seems to be the trapezium. Give you the better result, and the reason being that we are using both the information simultaneously. In the earlier case, we are using only this information and stretching in the interval. In the later case, we have using the final terminal value, and we stretch back into the interval. And in the case of trapezoidal method, we use both the value and take the average in that sense, and we are getting the better result. So this thing is clear. Anybody have any doubt? And this is also, this method is trapezoidal rule is also a implicit method, because unknown is sitting on the right hand side, and we don't have any procedure which can separate unknown and take on the left hand side, and everything on the right hand side is a given one. So that's why this is known as the implicit one. Hello, anybody have any query till here?
No, sir.
Good. So now if we talk about the order of convergence, order of convergence of these method. So how we do that? So can we do? Suppose we start here. We write that y I plus 1. So we start from the how to do the order of convergence. So should I clear that board? Ma'am, should I clear?
Yes, sir.
So now we will talk about the how to how to calculate the order of convergence. The method order of convergence, when we talk about the convergence of a numerical method for find the approximate solution of a differential equation. So there are two concepts. Before that, I should clear there are two concepts. Am I right? You might have heard consistency, consistency, or consistency, and the second one is stability. Stability. And anybody heard these two concepts? Anybody can answer? Anybody can tell something about consistency and stability? I think all of you must aware about about truncation error and round off error. Truncation error. Truncation error. Truncation error. Truncation error and round off error. Round off error. All of you are aware about that. And in the first lecture of numerical analysis, we generally do that. Truncation error. I call it human error rather than truncation error. Human error. And the second, I call it machine error. Machine error. Why we call it human error? Because when we talk about, as I told you that in the numerical analysis, basically the development of method to find the approximate solution of a mathematical problem. So why we do for the approximation? Because we don't have any methods, or there is our limitation. What is our limitation? We are not able to solve the problem, the mathematical problem exactly. So the error caused by this, caused due to the limitation of us, is known as the human error, or you might have heard truncation error. The limitation of humans to solve the exact problem is known as the, or gives rise to the human error or truncation error. Similarly, when we use any machine like calculator, computer, or anything we are using, so there is a limitation of machine also. The machine cannot store this number 1/3 exactly. Am I right? It's a non-terminating number. Floating point, when you will write its floating point representation, so it's a non-terminating. What value you will get? You will get 0 point. You will get 0.6 3 3. Yeah, it's repeated infinitely many digits it has. Am I right? So we don't have any machine which can store this number exactly. So after certain digit, we have to crunch these numbers. So and there will be a error because of that, which is known as the round off error or machine error, because it is it is happening due to limitation of machine. This thing is clear. So in this is in the general approximation theory. But when we talk about, so at every platform, we have to address these two errors. So when we address in the platform of the development of methods to find approximate solution of a of a differential equation, so the first error or human error is addressed by the concept consistency, and the round of error is addressed by the stability. Am I right? Stable. And when we say that the convergence of a method for the differential equation, so then consistency plus stability gives rise to the convergence. So this thing is clear. Any doubt in these two concepts?
No, sir, it's clear.
Yeah. So it means that now what is our objective? Our objective in certain, how we do work in a approximation theory. Generally, what we do, basically we we make a sequence of approximation, and in some limiting case, we say that that sequence of approximation converges to zero. Sorry, converges to the exact value. This thing is clear. Or we can say that in the certain cases that the error should be, in certain limiting cases, the error should converge to zero. So what is error? Basically the part which we are living when we are solving a problem, that should converge to zero in certain cases. So that gives rise to the consistency. So now the first thing here, that if you observe in the case of when we solve this a non-linear equation, fx equal to 0, I think all of you must aware about that, how we solve that using some approximate method, like suppose we are solving this by a Newton's method. So then we are getting a sequence of approximation xi. Am I right? And xi is given by the formula xi is equal to xi or xi plus 1, because I have to write xi many times. Xi plus 1 is equal to xi plus fi, f at xi. I'm denoting this fi divided by f prime at xi, which I am calling fi prime. The first derivative of f at xi. Am I right? So this by this formula we generate this sequence of this converges to, if we obtain xi, if we generate this sequence by this formula, so then this sequence converges to the exact root of xi, which is the exact root of this nonlinear equation fx equal to 0. So first we have to make when we are taking developing the approximate method to solve the differential equation in general, I'm talking about. It is true for boundary value problem as well as partial differential equation or any differential equation when we talk about. So then we have to generate a sequence of approximation. So how we generally do that in the case of differential equation? Anybody can answer? Any participant? Basically, when we are, I mean, the first thing we are approximating, in the sense we can say that we are approximating the continuous. First thing what we are doing, we are first thing when we are discretizing. Suppose this is our A to B is our domain. A to B is our domain. So the first thing what we are doing, we are approximating this continuous interval by the nodes, finite number of nodes. Am I right? The first approximation which we are making that. So rather than now, if we talk about that, the y, what is yx? Yx is a function which is defined on a interval A to B. Now what we are doing, basically we are approximating this y continuous function by a discrete function. Am I right?
Yes, sir.
Yeah. So that we are making that. So here, rather than so what type of sequence we have when we are I mean dealing the differential equation? So we have the sequence of vectors or discrete function, we can say that. Am I right? We will have a sequence of discrete function. Here yn is nothing but yn is a discrete function. Yn is a vector whose component are what are y0, y y1 dot. So the first thing here, it will not be a sequence of numbers. It will be a it has a I mean the discrete function. Am I right? So now how we will make that? Because here this sequence basically on I. So here it will be on n. Now if we make increase number of node. Now suppose we increase n. So this nodes will be, next term will be 2n, or n will increase. So this will be on the n1. And in the limiting case, what would happen? In the limiting case, this will converge. This will converge. Just conclude, please. So this will converge basically as we increasing n. So this I mean the discrete domain will converge to the continuous. I mean as n tends, sorry, as this n tends to infinity, as n tends to infinity. So this discrete domain converges to or cover exact continuous domain AB. Am I right? And this function of I mean discrete sequence of discrete function converges to the exact or continuous function yx, which is a solution of the differential equation or initial problem. This thing is clear. As n tends to infinity, or you can say that the h tends to 0. Both are the same thing, because as n in number of node will increase, so of course this space, I mean mesh size will decrease. So in that way we generate. So first we should understand this. So already I think we have time is over because I have some other appointment.
Yes, sir. Yes. You can conclude.
Yeah. So please, please.
Yeah.
So if anybody have any
Thank
doubt,
you, sir. Thank you.
I can.
Anyone has any question can ask.
Yeah, quickly. Otherwise, we can.
Any
take-
participants? Moderator, have you seen any questions in chat?
Ma'am, no, ma'am, no question.
Okay,
in
okay,
chat box.
okay, sir.
Okay,
You can
so
Thank you very
Anil
much.
ma'am, today I will send you one assignment. so
Okay,
that
sir.
and circulate to the student.
Sure, sure.
Okay. Okay. Bye.
Thank
Thank
you.
you.